Picture this: a massive planet floating in space and a tiny virus particle invisible to the naked eye. What could these two completely different things possibly have in common? The answer might surprise you. When scientists describe the mass of Earth, they write it as 5.97 times 10 to the 24th power kilograms. And when they measure the size of a virus, they write it as 1.2 times 10 to the negative 7th power meters. They both use negative exponents. These powerful mathematical tools help us represent both incredibly small and incredibly large numbers in a clean, efficient way. In this video, you'll discover how negative exponents work, why they're so useful, and how to simplify them with confidence. Whether you're dealing with atomic particles or astronomical distances, mastering negative exponents will give you the power to handle any mathematical challenge. Before we dive into solving problems with negative exponents, we need to understand exactly what they are and why they matter in mathematics. A negative exponent is fundamentally different from a positive exponent. While positive exponents represent repeated multiplication, negative exponents represent repeated division, or more precisely, they give us the reciprocal of the base raised to the corresponding positive exponent. To see this clearly, compare positive and negative exponents. 2 to the third power equals 2 times 2 times 2, which is 8. But 2 to the negative third power equals 1 divided by 2 to the third power, which is 1/8. Understanding negative exponents is crucial across many areas of mathematics and science. They're essential in algebra for solving equations, in scientific notation for expressing very small numbers, in engineering and physics for calculations involving rates and decay, and for simplifying complex mathematical expressions. For instance, the decimal 0.001 can be written as 10 to the negative third power in scientific notation. And in algebra, you might encounter equations like x to the negative second plus y to the negative first equals 5. Throughout this video, we'll master the fundamental rule for negative exponents, learn how to simplify expressions step by step, and identify common mistakes to avoid. By the end, you'll feel confident working with negative exponents in any mathematical context. Now that we understand what negative exponents are and why they matter, we're ready to dive into the fundamental rule that governs how they work. Now we're ready to combine negative exponents with one of the most fundamental exponent rules, the product of powers rule. This is where things get really interesting, and you'll see how negative exponents follow the same logical patterns as positive ones. First, let's quickly review the product of powers rule. When we multiply two terms that have the same base, we add their exponents together. For example, x to the third times x to the fifth equals x to the eighth, because we add 3 plus 5. The key insight is that this rule works exactly the same way when negative exponents are involved. We still add the exponents, but now we're adding negative numbers, which means we're actually subtracting. Let's work through our main example step by step. We want to simplify x squared times x to the negative fifth power. Remember, we add the exponents, 2 plus negative 5. Now we apply the product rule. We add the exponents, 2 plus negative 5 equals negative 3. So we get x to the negative third power, but we're not done yet. Remember that x to the negative third means 1 over x cubed. So our final answer is 1 over x to the third power. Let's try another example to make sure we understand this concept. How about a to the negative 2 times a to the fourth? We add negative 2 plus 4 to get a squared. Here's a more challenging example. What about y to the negative 3 times y to the negative 2? We add negative 3 plus negative 2, which gives us negative 5. So we get y to the negative fifth, which equals 1 over y to the fifth. The key takeaway here is that the product of powers rule never changes. Whether your exponents are positive, negative, or a mix of both, you always add them together. The negative signs are just part of the numbers you're adding. Remember, when you see negative exponents in multiplication problems, don't panic. Just follow the same rules you already know. Add the exponents, handle the negative signs carefully, and convert to positive exponent form at the end if needed. Now that we understand how negative exponents work, let's explore one of their most important real-world applications, scientific notation. Scientists and engineers use negative exponents every day to describe incredibly small measurements. Scientific notation is a way to express very large or very small numbers using powers of 10. The general form is a times 10 to the power of n, where a is between 1 and 10, and n can be positive or negative. When n is negative, we're dealing with very small numbers. The negative exponent tells us how many places to move the decimal point to the left, which creates numbers smaller than 1. Let's look at our first real-world example, the size of a virus. A typical virus is about 100 nanometers in diameter. In scientific notation, this is 1.0 times 10 to the negative 7 meters. To convert this to scientific notation, we start with 100 nanometers, which equals 0.00001 meters. We can rewrite this as 1.0 times 10 to the negative 7 meters. Notice how the negative exponent negative 7 tells us that we moved the decimal point 7 places to the left from 1.0 to get 0.00001. This is exactly what our negative exponent rule predicts. Now let's look at an even smaller scale, the distance between atoms in a crystal. This distance is typically about 2.5 angstroms, which equals 2.5 times 10 to the negative 10 meters. Converting 2.5 angstroms to meters, 2.5 angstroms equals 0.00000000025 meters, which we write as 2.5 times 10 to the negative 10 meters. The negative 10 exponent indicates an incredibly small distance. Let's visualize the incredible difference in scale. If we compare these sizes, we can see how negative exponents help us work with measurements that span many orders of magnitude. This is the power of scientific notation with negative exponents. It allows scientists to work with measurements from the cosmic scale down to the subatomic level, all using the same mathematical framework we've been learning. Whether you're studying biology, chemistry, physics, or engineering, you'll encounter scientific notation with negative exponents regularly. Understanding this connection helps bridge the gap between abstract mathematics and real-world applications. One of the most valuable habits you can develop in mathematics is always double-checking your work. This is especially important when working with negative exponents, where small errors can lead to completely incorrect answers. The best way to verify your negative exponent simplifications is to substitute your simplified answer back into the original expression and check that both expressions are equivalent. Let's see this verification method in action with a simple example. We'll start with x to the negative 2 power and verify our simplification. We simplify this to 1 over x squared using our negative exponent rule. Now let's verify this is correct by substituting x equals 3 into both expressions. In the original expression, 3 to the negative 2 equals 1 over 3 squared, which equals 1 over 9. In our simplified expression, we substitute x equals 3 to get 1 over 3 squared, which also equals 1 over 9. Both expressions give the same result, confirming our simplification is correct. Let's try a more complex example to really see the power of this verification method. Consider the expression 2x to the negative 3 power. We simplify this to 1 over the quantity 2x to the third power, which equals 1 over 8x cubed. Now let's verify with x equals 2. The original expression becomes 2 times 2 to the negative 3 power, which equals 4 to the negative 3 power, which equals 1 over 64. In our simplified expression, we get 1 over 8 times 2 cubed, which equals 1 over 8 times 8, which equals 1 over 64. Perfect match. Our simplification is verified. This verification method is especially valuable because it can catch errors before they become bigger problems. Make double-checking a habit in all your mathematical work. It's one of the best ways to build confidence and accuracy in your problem-solving skills.